Hello. It's been a while since I've spoken a video, though this one is a little different from my usual for talking. For the uninitiated, I've been working on a game called Ventury, which is inspired by a lot of titles from yesteryear. The most notable example is Ocarina of Time, and I'm sure you can see that. While the game has other influences, those are not so central to the topic of this video. Maybe next time I talk, I can discuss those. Anyways, something that has always stuck out to me for Ocarina of Time and its direct sequel is its implementation for shadows. Link, Stalfos, Dynalfos, and Lizalfos all make use of an interesting visual effect to fake shadows. Let's discuss how the game likely handles their shadows. Little disclaimer, I am cheating. Kind of. The Nintendo 64 likely wouldn't handle projectors like Godot's decals very well, and if we turn to our example, they're definitely not using projectors. For the mobile render method, Ventury uses a more old-school implementation, in large part because the mobile render method cannot accept more than 8 projectors at once, give or take. This isn't exactly the topic of the video, so I will return to our modern teardrop shadows. Before we start, we need a graphic for our shadow. Once we have the graphic, we can move on to how we draw that shadow to the screen. In my case, Godot has a special visual instance called a decal, which projects an image onto intersecting geometry. Since we're expecting to draw shadows on levels, we can set the visual layer to a different value so the decal can be drawn onto the level geometry without it also drawing on top of our characters. Our decals and levels need to share visual layers, but our decal and characters cannot. With that out of the way, we can get on to the more interesting technical stuff. Firstly, we need to get a point light's position relative to our character. We can figure what angle the light is traveling to hit our character and use that to change the angle of our shadow. While that looks fine enough if the light is being cast relatively low to the ground, it doesn't look so good when the light is higher up. We can fix that by adjusting the size of the decal with some snazzy maths. Using vectors in 3D space is our friend, and we can derive a lot of interesting effects or behaviors with the use of them. While this is all very interesting, we're actually missing one crucial component of our shadow casting algorithm. We are going to need to take a look at a formula in individual pieces, though we are going to cluster these into thirds, as our formula is a compound of 3, which, when combined, makes the shadows disappear with the following. When the object is very near the vertical global position of the light, it fades out until it matches the height of the light source, vanishing completely. The energy of the light source has an impact on the opacity of our shadows. And finally, the opacity of our shadows are again impacted by the attenuation of the light source. We need the shadows to become more transparent as the object travels away from the light source. Let's discuss that last one a little more closely. First, what is attenuation? I heard that term once in high school, but what does that actually mean? To quote Wikipedia, in physics, attenuation is the gradual loss of flux intensity through a medium. For example, dark glasses attenuate sunlight, lead attenuates X-rays, and water and air attenuate both light and sound at variable attenuation rates. So then if attenuation must mean that something loses intensity when traveling through some medium, such as water or air, then our attenuation for the point light here must be the same thing. If that's what it is, how can we mathematically simulate what Godot uses to alter the intensity of the point light here in our code? Enter the ease function. I'm not going to pretend to be smart, I just know that it can be used to create curves and to sample them at ranges of 0 to 1 inclusive. Knowing what it does under the hood though, I'm sure we can all appreciate how lucky we are not to create functions like this when we have one in the engine to start with. So we can use the ease function to simulate the attenuation of the point light's intensity as the light travels further from its origin, multiply that with the intensity of the light's energy, and also account for height to prevent any weird shadows. Even though we have ourselves a mathematically banging shadow casting formula, we have a bit of an issue: scalability. Our formula is probably correct. I mean, I'm not a math major or anything, but it is monumentally expensive. I tried everything I could to make my shadows more performant with multiple sources and many more objects which cast shadows, but nothing really seemed to stick for a while. For example, I offset when objects update their shadows, just how Blargis had suggested a little while ago. Doing calculations like this on a frame bus is not unheard of, and is a very old trick. This kind of stuff goes all the way back to the 80s. But even this didn't quite fix the issue. I made it so when the objects which cast shadows aren't on screen, the shadow calculations are extra throttled. But this still didn't fix the issue. I made it so the function does a few extra checks to ensure that the object is actually within range to cast the shadows before doing the expensive formula. This sort of worked, but it didn't fix the issue of needing to account for multiple sources at once, with some of them being invisible or so far away as to being completely irrelevant. My first attempt at an optimization was to create a blacklist of shadow casters for objects to evaluate for themselves. For this to work, it needs to prevent faraway lights from being counted in the shadow casting logic, and prevent lights which are not visible in the scene tree from being counted in the shadow casting logic as well. This blacklist should be updated relatively periodically, so we can put this on a frame bus just like we tried before. Every 20 physics ticks sounds nice, so on average we'll be making a blacklist every third of a second. This saved performance a good deal. I can fight 4 skeletons at once and have my companion with me without losing many frames. But this still doesn't do nearly as much as I'd hope, because the whole time we've been calculating this per shadow, not per source. To fix this incredibly old issue, I decided to make a cache that stores the results of our first calculation. The size, angle, and opacity of our shadow is encoded into a vector3 as its x, y, and z components. The cache is a typed dictionary that accepts our fancy node as a key and has vector3s as values. How handy. When we want to retrieve from the cache, we use the shadow's light source as the key, and if it returns nothing, we calculate the shadow and store its result into the cache. If it was already cached, we just set everything up without doing the expensive calculations, then continue to the next shadow. And finally, we keep this cache outside of the scope of the function to draw shadows, so that when Godot ever nosedives in terms of performance, we don't do double duty and just pull from the cache. We will only ever wipe the cache if the game draws something to the screen by calling clear on the dictionary in the process function. I hope this has illustrated how sometimes our simple ideas can turn up to being the genesis of a wild bantha chase. I also hope that you enjoyed the video. If you're interested in trying out the game for yourself, there's a link to the game's itch.io page in the description. There isn't a lot of content, if any, but there's plenty to take a peek at with the command bar. Oh, and the game is made for controllers. Sorry, keyboard people. Thanks for watching.